It will stop at 12:37.
Oh, sounds good. Okay, so I want to tell you today about some work that we've been doing recently to try and understand the bulk properties of higher order topological insulators a little bit better. I'm going to mostly focus on weakly correlated systems, but I think that the story that I have to tell you will point the way towards some interesting experimental and theoretical challenges when we want to think about correlations in these systems as well. So here are my collaborators. In particular, I want to highlight my student, Kwon Sun Lin, who's actually across the street as a KITP fellow right now. If I don't get through everything, or if you want to know more, here's the archive reference for the paper, and here's a GitHub link for some of the numerical tools that we developed for computing these topological invariants and type binding models. So I'll start with a review of higher order topological insulators, which I'll call HOTTIs for short. I'll talk about HOTTIs with gap surfaces in a case where we really do have a good understanding of what's going on in the bulk, and those are so-called magnetic Axion insulators. Then I'll talk about bulk probes in non-magnetic systems, where I'll introduce this new idea of spin-resolved topology, and I'll talk about our applications of this new method to alpha bismuth bromide, which is a higher order topological insulating candidate. Okay, so higher order topological insulators emerge when we have the combination of symmetry and topology in condensed matter systems. Symmetry sort of serves two purposes for us. It can both protect new topological crystalline phases, and it also gives us simple diagnostics for telling whether or not a given material is topologically trivial or topologically interesting. And this momentum space symmetry picture is dual to a position space picture, where we can think of topological insulators as systems where, if you look at the occupied bands and try and come up with some localized Vonnier-based description, you can't. Your Vonnier functions, for topological reasons, are extended rather than exponentially localized. And this framework of topological quantum chemistry gives us a way where we can take a crystal structure, a band structure, compute symmetry indicators and invariants, and diagnose topologically interesting materials very quickly just from knowing some momentum space symmetry data. But this diagnostic doesn't immediately tell us anything about what we should do if we have one of these materials. What should we go look for? What should we try and measure? And that's what I want to talk about today. So I'll just briefly review higher order topological insulators. These arise when we have crystal symmetry protected topological states that don't necessarily have these nice Dirac cones that we usually think of for topological insulators. With symmetries like inversion symmetry or roto-inversion symmetry, you can have topological boundary states that are not gapless surfaces, but instead in 3 dimensions lead to gapless one-dimensional modes on the surface of systems in some highly symmetric geometries. So here's a sketch of all the different roto-inversion symmetries that can protect these hinge states. You can see it shown in blue here. Imagine I have a sphere of crystal with perfect inversion symmetry. If it's a higher order topological insulator, it'll have some gapless mode that propagates along some great circle on the sphere. And the way that we can tell whether or not we have one of these materials is by computing symmetry indicators. We look at the high symmetry points, we compute the, in this case, inversion eigenvalues of the occupied bands, we compute an integer, and if that integer, in this case, is 2, we have a high order topological insulator. But there is a little bit of a problem with this nice theorist picture. I can tell you that I have these hinge states if my entire finite system preserves the inversion symmetry of the crystal. And real systems don't look like this. Real systems aren't perfect spheres that I can draw. They have defects and disorder on the surface. And the problem with these one-dimensional hinge states is there's lots of ways to get one-dimensional modes on the surface of some 3-dimensional system. I can have little step defects, and those can have modes that propagate around. I can make defects on the surface that move these hinge states around. And if I let myself break the symmetry by, say, adding another layer to the surface, or that layer happens to be a two-dimensional topological insulator, I can actually go from something that doesn't have hinge states to something that does, just by wrapping the system with a two-dimensional topological phase. What this means in practice is that high-order topological insulators have hinge states usually, but not everything with hinge states is a high-order topological insulator. So what can we look for to definitively experimentally diagnose this higher-order topology? And the place I want to look is, oh yes.
In your definition, you are only considered second order, right? Because if I had, or third, because
Second,
because in principle I could have also a 3D material that has corner states if it is second order. Sorry.
so we can get into some terminological issues about whether or not order in that sense is necessarily the best way to think about things, but yes, I'm talking about 3D systems with hinge states, 2D systems with corner states, and 3D systems with corner states actually, with only crystal symmetries, do allow for exponentially localized Wannier functions, and so there's a separate story that we can talk about.
So it's a definition. It's a definition. Yeah.
So I want to look at the bulk of the system. And what we can do is ask about these Wannier functions. We can ask where do the electrons inside the bulk of a higher order topological insulator, where do they live, or where can we localize them? And I'll ask this question by introducing hybrid Wannier functions. I'll take my block states that are extended throughout the whole crystal, and I'll try and do some Fourier transform to try and localize them as much as I can in one direction, and let them still depend on be indexed by momentum in the perpendicular direction. Schematically, I'll go from some extended block wave like this to something that's a wave packet in one direction and extended in the others. I'll call the direction where things are localized the parallel direction, perpendicular directions are the others, and these hybrid Wannier functions, I can make them, and they're centered at some positions Rn in the unit cell indexed by the parallel direction. And the center Rn can actually depend on this perpendicular momentum. In boring, I'll say boring, topologically trivial systems or atomic insulators, I would expect if I make these functions, well, in an atomic insulator, atoms don't really talk to each other. Everything's flat as a function of momentum. I would expect these centers to all also be basically around the same point. To compute these hybrid Wannier centers, we can use a non-abelian Berry phase, or sometimes called a Wilson loop. In practice, what we do is we compute some band structure. We look at the occupied bands and their eigenstates, form some projection operator onto those states, and just multiply them together in a path along the parallel direction. This gives us some big matrix W, which has the nice properties that the eigenvalues of this matrix, or the log of the eigenvalues of this matrix, tell me the centers Rn of my hybrid Wannier functions, and the eigenvectors of this matrix allow me to construct these functions themselves. Basically because this matrix is related to the position operator projected into this set of bands.
Question. Is this operator in the products basis of all the k-states? Does it act on all k-states simultaneously?
No, so these projectors are the projectors just onto the states at 1K.
But it's a product of them.
It's a product of them, but it's a product of them from some starting point to that starting point plus a reciprocal lattice vector.
Yes.
So it's actually a matrix that acts on states at this base point K0. Now, what is non-trivial, and I haven't proved, but is the reason that this is useful, is the eigenvalues actually don't depend on the parallel component of this base point, but the eigenvectors do, and this lets me construct a whole family of Wannier functions in each unit.
But it's an outer product of P of K's.
P is an outer product of U's, this product is an inner product. So if you like, I can take matrix elements of this operator, and then it's a product of overlap matrices, if that makes it more clear. But it is an inner product.
If you need,
Oh, maybe at the end we can circle back to that. If I look at these centers and how they depend on the perpendicular momentum, I can compute topological invariants. So one interesting thing that can happen, if I'm plotting here these centers, the z component of my hybrid Wannier centers as a function of perpendicular momentum that I'll call ky, you can see in this panel here what happens is I have at each k one hybrid Wannier function per unit cell, and as I move ky, these functions shift from one unit cell to the next. If I take ky from 0 to 2 pi, I move by 1 unit cell. And this movement by 1 unit cell tells me that this band structure with these hybrid Wannier centers has churn number 1. Physically, one way you can move ky is by applying an electric field in the y direction. And this is telling you that if I apply an electric field in the y direction, charge is going to adiabatically shift in the z direction. This is the anomalous Hall effect coming from this churn number 1 in a churn insulator. Can look at hybrid Wannier centers for time reversal invariant phases too. For a Z2 topological insulator, I get something like this, where I have one band of hybrid Wannier states with this flow like it has churn number 1, and then its time reversed partner going in the opposite direction. Thing that distinguishes these from a topologically trivial system is that there's spectral flow in the spectrum of hybrid Wannier centers. I can't flatten these out. Here I can't flatten things out at all. Here I would have to break time reversal symmetry to break this degeneracy and have different hybrid Wannier functions that are time reversed partners centered at different points. Okay, so what I want to do now is apply these ideas to understand what's going on in higher order topological insulators, and I'll focus on the simplest case just protected by inversion symmetry. So these systems can be understood by starting with a 3-dimensional topological insulator with inversion and time reversal symmetry, and either breaking time reversal symmetry while preserving inversion, so some bulk antiferromagnetism, for instance, or by doubling the band structure of the system, or if you'd like, having a double band inversion instead of a single band inversion, while preserving both symmetries. So we want to ask what's going on in the bulk of these systems that distinguishes them from trivial insulators. I'll start with this time reversal breaking case because we understand it pretty well. So we can tell that this system, where I have an antiferromagnetic topological insulator, is topologically non-trivial by computing symmetry indicators. We look at the occupied band inversion eigenvalues and count how many minuses we have. The hinge states, though, can be gapped out by breaking inversion symmetry on the surface. The bulk of these systems, though, we know from a low energy effective theory point of view and from some seminal work from a decade and a half ago, that the bulk of this system, because it comes from a 3D topological insulator with broken time reversal symmetry, has this Axion electrodynamics type response. There's this theta that's called the Axion angle, multiplies E dot B in the Lagrangian, and this tells me that this system has a magnetoelectric polarizability. I apply an electric field, or apply a magnetic field, let's say, and generate an electric polarization. And this coefficient theta, which in an ordinary 3D TI we think of as being quantized by time reversal symmetry, here it's still quantized by inversion symmetry. What this means for the surfaces, if I look at this field theory and look at what happens when I go from a topological insulator to a trivial insulator, this theta jumps and it leads to these gap surfaces, which no longer have any hinge states, having a half integer anomalous Hall conductivity, which is not something you can have in an isolated 2-dimensional system. By looking at the hybrid Wannier states, we can actually come up with a much more concrete picture of where this half-integer surface Hall conductivity is coming from. Can take a tight binding model for magnetic higher-order topological insulator, and we can compute its Wilson loop and look at the hybrid Wannier centers. Here we have them, the hybrid Wannier functions localized in the z direction, centers as a function of ky for 3 different kx values. And what you see is that there are some hybrid Wannier states localized near the origin of the unit cell in the z direction. They'll label P in here. And then there's some that are localized near the boundary of the unit cell in the z direction. And these are the 2 inversion symmetric planes in the unit cell. So let's focus on these states centered near z equals 0. We can take those hybrid Wannier states and we can ask, what is their topology? What happens if we take those states and compute their baryphanes? We can do that for either the inner states or the outer states. And that tells us something about what is the topology of the electronic states living near the origin or the boundary of the unit cell in this system. What we find is that the hybrid Wannier centers for the states living near the z equals 0 plane in the occupied states have churn number 1. And the hybrid Wannier centers for the states living in the z equals 1/2 or c over 2 plane have churn number -1. This gives us a concrete picture for how we can construct something that has the same topology as this magnetic Axion insulator. We stack layers of c equals churn number 1 and churn number -1 layers. The churn number 1 layers at the z equals 0 inversion center, churn number -1 layers at the z equals 1/2 inversion center, and we just continue that for infinity. So what happens if we have a surface? Well, there's two perfect surface terminations that I'll focus on here. One where we have our c equals 1, -1, 1, -1, 1, -1, but we end in an inversion symmetric way. And in this case, the churn number at the bottom surface, where the normal vector's down, is 1/2. You see there's one missing layer here. Churn number here is also 1/2. There's one missing layer. So in a coarse grain sense, the churn number between these two surfaces, because of the change in the normal direction, jumps by 1. And this leads to a hinge state on the boundary, because the churn number changes by 1. But I can add an extra layer to this top surface, and then I can get rid of the hinge state that way. But now what I have is surfaces where, on average, the churn number is 1/2 on the top surface, -1/2 on the bottom surface, 0 total. This is not something that I could get in an isolated 2-dimensional system. I can never have an insulator with churn number 1/2. And this leads to the half-quantized surface anomalous Hall effect and the anomalous K rotation in these systems.
So just to clarify,
Yeah.
when you say surface, you mean literally the surface of the sample? Or do you mean?
I'll show a plot in a little bit. It's the surface of the sample, but average some number of unit cells into the bulk. So I really mean the surface of the sample,
Okay.
but not necessarily one atomic layer. It can be.
So the top and the bottom of the sample would have opposite churn number?
Yeah, so what you can actually do, and there's a plot later related to this, you can layer resolve the churn number and plot the churn number density as a function of layer, and it sort of exponentially starts high, exponentially decays into the bulk, is 0 throughout the bulk, and then goes back up. And the total churn number in the region where it's not 0 is 1/2 on the top surface and -1/2 on the bottom.
Okay.
Okay, so let's try and apply this to time reversal invariant systems. In time reversal invariant system, the symmetry indicators tell me that this Axion angle theta is equal to 0 mod 2 pi. There's no quantized magnetoelectric effect in these systems. But we can play the same game that we just played with hybrid Wannier centers. Take a model for a helical HOTTI and look at its hybrid Wannier states Again, we see because there's inversion symmetry, some of the hybrid Wannier states are localized near the origin of the unit cell, the z direction. Some are localized near the boundary. And we can focus on those separately and look at what their topology and their varied phases are. And we find that the states near the origin of the unit cell have hybrid Wannier spectrum that matches that of a 2D topological insulator with time reversal symmetry. The states at the boundary of the unit cell also look like a 2D topological insulator from the point of view of their Wannier centers. And so we might think then, well, maybe we can construct a higher order topological insulator by stacking layers of a 2D TI in an inversion symmetric way. But now these two layers are the same. It's a lot harder in this picture to see what's special about this other than just it being a weak topological insulator. To answer that question, what the perspective we took is to remember that there's more going on with electrons than just their block states. Electrons also have spin. We choose to focus on spin in particular because every electron in the universe has spin 1/2. It doesn't depend on what model we're considering or what material. It gives us something that we can look at. And so what we can do is take these occupied bands and look at the matrix elements of the electron spin in these occupied states. This gives us an operator that I'll call PSP, or the projected spin operator. If spin were conserved, so if these occupied states were all spin eigenstates, then if I plotted the spectrum, I'd see a bunch of 1s and a bunch of -1s in units of h⁻². These systems have spin orbit coupling, so I don't see that. I see, some wiggles, some band structure. But the key insight that goes back to Prodan is that these bands, if spin orbit coupling doesn't actually even have to be weak, except in exceptional cases, we'll still have some bands that have mostly negative spin eigenvalue and some bands that have mostly positive spin eigenvalue. We can be a little bit more precise about that. This spectrum of the spin operator also depends continuously on the spin orbit coupling and parameters of the Hamiltonian. It's really a gauge invariant object. It changes smoothly when I perturb the Hamiltonian, and that means that it's something that I can look at. So what we can do for a 2D topological insulator, even with spin orbit coupling, is we can focus on the states with, say, mostly negative spin, compute their churn number, gives us something we'll call C-. You can do the same for the states of C+. And the 2D Z2 invariant is actually given by either of these mod 2. They're actually equal and opposite if you have time reversal symmetry. Their difference defines what's called the spin churn number. And if spin is conserved, the spin churn number gives the quantized contribution to the spin Hall effect. But even when spin's not conserved, we can do this. And we can take all of the machinery we just developed. We can look at these mostly spin up states, look at the hybrid Wannier states we can make out of just the mostly spin up electrons and ask what their topological invariants are. And for a helical higher order topological insulator, we find that two things can happen, and it depends on the system. Either you can have this stacking of two DTIs where each of the two DTIs is identical, having the same spin churn number, so that there's a bulk spin churn number per unit cell that's not 0. And this is a phase that has been introduced by others previously, sometimes called a 3D quantum spin Hall insulator. They're the macroscopic system, there's a macroscopically large spin churn number. But more interestingly, you can actually have opposite spin churn numbers for these two DTI layers. And that's something we call a time reversal doubled Axion insulator, because it's like one copy of a magnetic Axion insulator I showed you before for the spin up electrons, and the time reversed copy for the spin down electrons.
So could this,
Neither of them is a weak TI?
Neither of them is a weak TI.
could this be generalized to superconductors?
Yes. So that's something that we are currently working on. There are, well, there's sort of two different paths you could take to generalize it towards superconductors. One that's very straightforward and one that's a little more exploratory, I would say. You could either look at the spin operator in superconductors, or you could try and do something similar with particle hole symmetry.
That's interesting.
There's another question.
I have to go now.
Oh, great, there it is. Okay, so here's the picture, and I'll just skip to say we can compute the layer resolved spin churn number and find that the surfaces are anomalous. And we can apply all of this to ab initio models. So we, with our collaborators, did some ab initio calculations on this quasi one-dimensional alpha bismuth bromide, which is a helical HOTTI candidate that, unlike so many materials that us theorists talk about, you know, you compute the band structure and there's actually a gap, and you experiment and measure it and there's actually a gap. And we can compute the spin resolved topology for different spin directions and the bulk intrinsic contributions to the spin Hall conductivity. And we see that this picture of these different spin resolved phases tells us something about the bulk contribution to the intrinsic spin Hall conductivity. Okay.
Thank
Great.
you.
Yeah.
The value for the spin Hall conductivity, is there anything quantized that is connected to the spin resolved?
No, so there are, the reason that this is not quantized is because spin is not actually conserved. So what you can do is you can write out the Kubo formula for the spin Hall conductivity and massage it a bunch, and what you get is you can write it as a contribution that's like E over 4 pi times the spin churn number, plus another term, a bunch of other stuff that you can prove vanishes if spin, that component of spin is conserved, but is general non-zero. And it depends sort of, the difference between this and the quantized value grows, at least in some simple models that we looked at, like the square of the spin orbit coupling string. But I should also say, this is the intrinsic contribution to the spin Hall conductivity. This does not include any of the equally important extrinsic contributions to the spin Hall conductivity.
Okay, I think in the interest of time, let's thank Barry again. And this session is closed. We have lunch.